Hi, this is Math 1650, and this video is going to start the chapter on probability. And it's going to be over section 4.1. And we're going to start with the very basics of probability, and so we're going to start with some definitions here. First, an event. An event is a collection of results or outcomes from a random experiment or procedure. A simple event is an outcome of an event that cannot be further broken down. Right, so definite couple example for each. Event would be rolling a dice, and your outcomes are you can roll a 1, a 2, a 3, a 4, a 5, a 6. A simple event is rolling a 3, or another simple event is rolling a 2. Okay, something like that, something that has a specific outcome. Sample space refers to the set of all possible outcomes of a random experiment. It consists of all simple events. Right. This is different because an event can also be, it doesn't have to be all possibilities. It could be rolling a 1, 2, or 3. It doesn't have to be all possibilities, whereas sample space is all possibilities. Okay. Now with some notation. P of A means the probability of event A occurring. So for instance, probability of rolling a 3. Okay, what the probability of that is. It's going to have some value that's going to be either ran as a percentage or a decimal or a fraction even. Okay. Events that are certain to occur, probability of certain event is going to be equal to 1 or 100%. Impossible events is going to be equal to 0 or 0%. The complement of A. This is the probability of A not occurring. So P of not A, which we also write as P of A with a bar above it, is the opposite of P of A. So it's equal to 1 minus P of A. Right, think about it this way. Probability of rolling a 3 equals 1/6. There's 1, 3 out of 6 possibilities. Not a regular 6-sided die. The probability of not rolling a 3 is 5/6. The opposite, there's 5 possible numbers that are not a 3 on the die. Right? And then together, 1/6 plus 5/6 equals 6/6, which equals 1. Okay, so the probabilities have to end up equaling 1. Right, so we have 1,010 United States adults were surveyed, and 202 of them were smokers. Okay, the event is adult being a smoker. Sample space is smokers and non-smokers. There's no real in between. And then probability of a smoker. Oh, I have it written, so I'm not going to rewrite it again. Probability of a smoker is 202 smokers out of the total 1,010 people. Probability of not having a smoker, well, 202 of them were smokers, then 808 of them were not. So it's 808 out of 1,010. And then we can do the math here. We can divide 202 by 1,010, you get 0.2, which can be written as 20%. Let's move the decimal 2 spots. And if you divide 808 by 1,010, you get 0.8, which is equal to 80%. And notice that these add up to 1 and these add up to 100%. Since smoker and not smoker are complements of each other. Alright, so we're going to use StatDisk to do some of the simulations here. So we're going to do 1,000 rolls on 2 6-sided dice. Right, now, before we do this, I want to just kind of go through, 2 6-sided dice, the possibilities here. You can roll a 2, you can roll a 3, a 4, a 5, a 6, a 7, a 8, a 9, a 10, 11, or a 12. Let me bring back the zoom. Right. The only way to roll a 2 is a 1 and a 1. The only way to roll a 3 is a 2 and a 1 or a 1 and a 2. Okay, go down to the 12. The only way to roll a 12 is a 6 and a 6. The only way to roll 11 is a 5 and a 6 or a 6 and a 5. Right, for 10 and 4, there's 3 possibilities. For 4, you can roll a 3 and a 1, a 1 and a 3, or a 2 and a 2. For 10, you could roll a 4 and a 6, or a 6 and a 4, or 5 and a 5. For 5, there's 4 possibilities. For 6, there's 5 possibilities. And 8, there's 5 possibilities. And for 7, there's 6 possibilities. A 4 and a 3, a 3 and a 4, a 2 and a 5, and a 5 and a 2, 1 and a 6, and a 6 and a 1. So the probability of getting an 8 would be 5 out of 36. You add up all of these possibilities, you get 36. And 5 out of 36 comes out to be a 0.139. For this, we're going to simulate it with the dice. 1,000 rolls to see how close we get to that. So to do a dice simulation, you go dice generator at the bottom of the data tab. You can put in 1,000 tosses, 2 dice. I don't know why 10 is the default. That's kind of odd. 6 sides, and then select the column, generate. Right now, it gives us all sorts of numbers, and there's 1,000, and we do not want to go through and count every one of these. So the easiest way to do it is to actually go up to the histogram, select the column. I like to start mine at 0, width of 1, and plot. And so this is your 2, your 3, your 4, your 5, your 6, your 7, your 8, your 9, your 10, your 11, and your 12. And we can see that it, just like our how many possible ways, this follows the same kind of pattern. There's less 2s that come up and less 12s that come up, but they're kind of close to the same. 11 and 4 is about the same. 4 and 10s are about the same. 9 and 5, 6 and 8 are about the same, and then 7 is the highest. So we were looking at 8, so we got 138. So the probability of getting an 8 based on this is 138 out of 1,000, which is 0.138. Okay, which is very, very close to our classical probability. Okay, the 0.138 is very close to the probability of 0.139. We can look at the simulations of 200 births using a coin generator. We're going to have boy be 0 and 1 be a girl. So let's do that. Now, go back to the regular data set. I'm going to clear this and choose coin toss. We're going to do 200 births. We're going to do 1 coin. So you get either 0 for a boy, 1 for a girl. Put that in column 1, generate. And in this we could actually just sort the data to see how many come up. We're going to count the number of boys, so we're going to count 0, so we want it from A to Z, so the 0 is at the top. Then we're looking to see where it ends. So we had 104 boys. So based on this, the probability of getting a boy would be 104 out of 200, which is about 52%. Very close to what we would expect, about 50%. Alright, so we're going to get into now some basic rules or methods of probability. And we kind of have seen these already, and so just in those last few examples even. The first one is the relative frequency, or the empirical, or I like to think about this, the experimental possibility. For a given sample, for a given simple event, A. There are S ways that event A can occur. Out of n possible outcomes. And the probability is the number of times A can occur, or the number of ways A can occur, and the number of trials that are done. And these are how many trials are actually done. So, for example, when we did the dice and rolling the 8 with 2 dice, we had 138 times 8 came up. Didn't matter how it came up, whether it's 4 and 4 or 5 and 3, it doesn't matter. 138 times we got a total of 8 out of 1,000. Oops, let me change the color on this. Out of 1,000. And so our probability is 0.138. For the butts, we had 104 boys come up out of 200. So the probability is 0.52. It's just based on testing it and flipping a coin, rolling a dice, running an experiment, whatever it is. If it's a medical test, it's just based on how many times you run the medical test to see the numbers coming up. That sort of thing. If you're testing your sugar and you want to see if it's, compare when it's high and when it's not. Maybe how many times your sugar is high in a day. You keep tally of every time you check. It's just something you do experimentally or something you actually perform. For the classical approach, or you can think of this as theoretical or actual probability or classical, this is based on mathematics. For a given simple event A, there are S ways A can occur. Out of n possible outcomes. Right. So number of times A can occur our total possible outcomes. So for 8, for rolling an 8 on two dice, we have 4 and 4, 5 and 3, 3 and 5, 2 and 6, 6 and 2. Right, so this was 5 times. Those are 5 ways. So S is 5. We have 36 total possible ways. And so that's our classical probability, 0.139. For the coin flip, and we have boys and girls, we have a 0 for a boy, which is 1 way, and there's only 0 and 1 as the possibilities, so it's 0.5. I have these above, but I'll just do that. Got a little ahead of myself in where I wrote them. Right, the law of large numbers. As an experiment is repeated over and over again, the relative frequency approaches the classical probability. We saw that with those two examples with the dice. 1,000 rolls, and you have a probability of 0.138, which is very close to 0.139. Considering that one roll, you may get an 8, you may not get an 8, it's either going to be 0, which is not really near 13.8%, or it's going to be 100% and you get it, and 100% is nowhere near 13.8%. So, you know, the more rolls you do, the closer it's going to get to the actual probability. We also saw this with the 200 births. Usually, 50 to 100 can be a decent size sample to get a value that's pretty close. 100 is usually really when it starts to happen, and we're going to see that in this, hopefully, if it all works out, in this next example. So we're going to simulate the two-sided die again, but we're going to do this by changing the number of trials, and we're going to again look at it for 8. So I'm going to clear this data. We're going to go back to a dice generator. We're going to start with 10 trials, 2 dice, 6 sides on each dice, and the first column. Okay, so the first column is going to be 10, then I'll do 50, 60. I'm going to add a column here as well. Right, and then down the line, I'm going to do the generations first, and then we're going to look at the values. So first for 10, generate this in the column 1. Then we'll do 50. Generate this into column 2. Now we have to take out that number, otherwise it'll give us the same data set. And we do 100 in column 3. And we do 500 in column 4. Then 1,000 in column 5, and then 5,000 in column 6. Alright, if you're doing this, I'm following along and doing this as well, your numbers will be a little different, but they should be close to the same, especially towards the end. Right, so we're going to go to histogram. I'm going to select the first column, and I'm going to start this at 0, start the width at 1, and plot. And so again, this is 2, there was no 3s, 1 4, 2 5, 3 6s, 1 7, 0 8s, 1 9, 1 10. So we got no 8s given in this. So 0 is our number obtained. Right, let's go to each of these as we go through. Get the numbers down first. So here, 2, 3, 4, 5, 6, 7, 8. We had 12. So then for 100, 2, 3, 4, 5, 6, 7, 8. We had 12 again. Notice that these graphs are not all that great of a bell curve right now. This looks like a decent bell curve, a little high on this side. 74. Okay. Then 1,000. 1,000 doesn't look that good. Our number's gonna be a little bit off. 150. And 5,000. Let's hope that this is a decent bell curve. There we go. Pretty decent bell curve. 696. Okay. So let's look at these values. We're going to take each of these out of the total amount. So 0 out of 10, 12 out of 50, 12 out of 100, 74 out of 500, 150 out of 1,000, and 696 out of 5,000. Now some of these I can do in my head. 0 out of 10 is 0%. 12 out of 50 is 24%. 12 out of 100 is 12%. 74 out of 500 is 14.8%. 150 out of 1,000 is 15%. And 696 divided by 5,000 is 13.9%. Actual probability is going to be 5 out of 36, which is 0.139 or 13.9%. Alright, so it started off really bad. 0%, 24%, nowhere near the actual. It got closer at 100 with 12%. And it did get a little bit farther off at the 500,000, which I kind of did not expect, but that happens. But then it's right on target, right at 5,000. Right. And so as the number of trials increased, the simulated probabilities were closer to the classical probabilities with some fluctuation. No, I should say classical probability, not probabilities. The final simulation with n equaling 5,000 was right on target. This demonstrates the all large numbers by showing the relative frequency approaches the classical probability. There are proofs to this, mathematical proofs that show that this has to happen. But there is, again, fluctuation when we're testing things. So, something like 500 and 1,000 rolls, maybe a little bit farther off. We got kind of lucky at the 100 trial because it's probably closer. Actually, when we look at the difference, this is below 1.8%. This is above maybe 1%. This is above 1.1%. Actually, yeah, the 500 and 1,000 actually look closer, even though they look a little higher. They're definitely higher, but they look a bit farther than you would think. They're actually even closer than that 100 trial. But the biggest thing is at 500,000, this is 0.1 off. Okay. The last type of probability, which is not something we're going to look at a whole lot. That's subjective probability. This is the probability of an event, we're going to call event A, based on experience, knowledge, maybe even intuition. Basically, based on having lived, you have an idea that something's likely or not likely. All right, so let's look at an example. We're going to go through kind of a few different probability types here, but the last one's definitely going to be subjective. All right, we're going to consider an event to be unusual if its probability is less than or equal to 0.5 or 5%. This is usually a common criteria, but it's not absolutely rigid. A lot of times they use it in business because it's the best to kind of make sure you don't have a loss. But sometimes it can be adjusted and they use 0.1 or 0.01 or even weird values in a sense. Usually if it gets around 0.05, the researcher just has to make a decision what they're going to do. Right, so in this example, on their first date, Kelly and Mike, Mike decides he's going to try to guess her birth date, not including the year. And we're not going to worry about leap years. What is the probability that Mike guesses correctly? Well, one birthday. You only are born on one day out of 365 days. Okay, this works out to be a probability of 0.0027 or 0.27%, much less than 5%. Much less than 5%. Okay, so yes, it would be unusual, and she would think he knew somehow. And so if you or Kelly and Mike did guess correctly in his first try, would you believe his claim that he made a lucky guess, or would you be convinced that he already knew you when you were born? And again, you would be convinced he found out somehow. Assume he found out somehow, and not be impressed. The intuition there for her should be, this doesn't seem likely. If Mike wanted to guess her age and was off by 10 years, and yes, 10 years older than what she was, what are the chances of making a second date? This is subjective probability. Chances are very slim, if not zero. All depends if he could talk his way out of it. All right, so that's a little bit of example of some classical probability there with probability of guessing somebody's age or guessing somebody's birthday, and then a little bit of subjective probability there. Alright, let's do a couple more examples here. These are going to be a little bit more serious, I guess you can say. Alright, in a clinical trial of Lipitor, a common drug used to lower cholesterol, one group of patients was given a treatment of 10 milligrams of, I'm not even going to try to pronounce that word, tablets. That group consists of 19 patients who experienced flu symptoms and 144 patients who did not. Estimate the probability that a patient taking the drug will experience flu symptoms. So there's 19 patients, and then the total of this is 863. Total number of patients there. So you either experienced it or you didn't. And so your probability is 19 out of 683. Or 863. And you get 0.022 or 2.2%. Is it unusual for a patient taking the drug to experience flu symptoms? Yes. This probability is very low and less than 5%. It's likely that maybe they would just gain the flu and had nothing to do with the drug. It's basically what this is saying. Alright, we're going to do one last simulation here. This is going to use the coin toss generator again, and then we're going to look at some probabilities with it. We're going to toss 25 times. We're going to do this over 10 trials. We're going to be switching, I guess. 0 is a girl, 1's a boy. I think that's just so there's no, it doesn't really matter. So let's get rid of this data. I'm going to add on some columns though. I'll add on 5 columns. Alright. So coin toss. 25 times. Number of coins is 1. And we're going to put in the first column. And then when we keep doing this, I don't know how to take out the C number, but we'll just do it 10 times right off the bat here. Column 2. Column 3. Column 4. Column 5. Column 6. Column 7. Column 8. Column 9. And the last one. Column 10. We'll count the number of boys, so we're going to count the 1s in each of these. It's probably easiest to just do it by histogram since there's so many columns. So width is going to be 1. Start up at 0. You'll just see 2 columns, so you know which one's which. Right, so 10 in the first one. 14. 14 again. 13. 15. 10. 16. 10. 11. And the last column, 9. Right, now we're basing this on the 10 trial, so our probabilities are going to be out of 10 and not out of the 25. Notice that's a common mistake some people have made, is they're thinking each one is out of 25, but we're looking at the trials themselves. And so as getting exactly 14 boys and 25 births, that only happened twice. So it's a 2 out of 10. Getting probability of getting at least 14 boys. This means that you're including 14, 15, and so on. So that happened twice for the 14, and then a 15 and a 16. Everything else is under. So that's 4 out of 10. And then getting at most 14 boys, that means 14, 13, 12, and so on. It happens the 2 times, and then 3, 4, 5, 6, 7, and 8. You have 8 out of 10. Right, so you can write as a fraction, or you can write 20%, 40%, and the last one being 80%. Alright, so that's the end of section 4.1. In section 4.2 and 4.3, we'll start looking at some addition rules and multiplication rules when it comes to probabilities. I'll see you then.